Ladies and gentlemen, welcome to the third lecture from Calculus 1 with applications. In this lecture, we will talk about functions and graphs, and we'll see a bunch of properties for functions. We'll see also how to draw graphs for certain type of functions, what to look for when we draw graphs. But anyway, we'll cover this later on in the semester. Also, we'll be talking about trigonometric functions, about inverse trigonometric functions, and so on. Okay, let's get started. So I'm going to start with functions and graphs with something very easy at first. So functions and graphs. Okay, and let's start with functions first. Okay, so let's see what is a function basically. So a function. So a function. Let's say. Okay, let me put it this way. A function is a rule, let's say, that assigns each element x of the set, let's say big X, a unique element let's say y, unique element y of the set, let's say y, big Y. Let's draw the picture. So in other words, we have something like this. All right. So here we have the input. Let's say this is x, and here we have the function f, let's say, right? And here, so here's the input, we'll put it in, and we'll see how this will work with the function f, and then as a result, we'll have the output, which is this value y, which is f of x. Right? So this is the picture you have to remember. Anyway, we'll see later on in the lecture how to compute values of functions, of different functions. Anyway, okay, now the image. Let's talk a bit about the image. And here, I would like to say that the element y is called the image of the element x under the function f, under f. So that's what you have to remember. This is what we call y, right? Again, just look at the picture. We have the input, we put the element x, and then we evaluate this element x through the function y. In other words, and we'll obtain the value y, which will be f of x. So this element y is nothing else than just the image of x under the function f. Okay, and now let's talk a bit about the domain of a function. Before we go and dive more into examples, I would like to say a few words about the domain. All right, we have said that, and maybe I should have put it here, f defined on x with values in y, right? Because we said at the beginning a function is a rule that assigns each element x from the set x a unique element y of the set y, right? Okay, great. Well, in this case, the set x is called the domain of the function f. It's called the domain of f, of the function f, right? Okay, and we would like to say a few words about this. This is the set of real numbers for which the function is defined. That's what the domain is. Okay, let's point out this here. If a function is undefined at a particular x, it means that x is not in the domain of f, of the function f, right? That's what it means. If you cannot define that function at that particular value of x, then this means that that particular value is not in the domain of x. Well, we would like to say such values are called, let's say, domain restrictions. Right? And now let's see some examples. I'd like to show you some examples of functions with domain restrictions. And the examples I have in mind are the following. Let's start with the first one. For example, let me consider the following. Function f of x is 1 over x minus 3. And of course, x has to be different than 3. You know, for a fraction to exist, the denominator must be non-zero. In other words, since x is different than 3, so that this guy can exist, it follows that the domain of f is nothing else than just this union of intervals, negative 3, 3 open, and 3 positive infinity. Or in other words, this is nothing else than just the entire real line, where we can express this as negative infinity, infinity open, and we take out this element 3. We can write it in this way, right? Now let's see another example. Well, let's say another fraction b. Let me call this one f of x is 1 over x times x plus 2. Again, as you can see here, this is a fraction, and for this fraction to exist, I need to make sure that the denominator is non-zero. So in this case, x has to avoid the following two values. Well, the denominator is 0 if x times x plus 2 is 0, so which means in this case, x has to be different than 0, and x plus 2 has also have to be different than 0, which implies that x is different than 0 and x is different than negative 2. So this is x is different than 0 and x is different than negative 2. And the domain of f is nothing else than just, well, if you want to write it like this, it's negative infinity 0, negative 2, union with -2, 0, open interval, and then open interval 0 and positive infinity. You see, this is the domain is the union of the 3 intervals. In other words, if you want to write it, you can write it in this way. It's -infinity, infinity, and you exclude here these 2 values, -2 and 0. Basically, it's just the entire real line where you take out those 2 values, -2 and 0. Now let's see another function. And then the other function that I have in mind is not going to be a rational function like the previous 2. It's going to be the square root of x. Well, there is one thing that you need to know about this function, and we will use it over and over again throughout the semester. And the thing that you need to know is that, and I'm going to write it, that let's write it in this way, the x values how should I say it, are non-negative under the square root. Or, okay, in other words, let's translate this. This means that the domain restriction, you cannot have negative values inside the square root because we'll deal with some different numbers, with complex numbers, right? And we don't want to deal with that. So we're dealing only with the real numbers. So if you want to deal with the real numbers, the only option you have is that the values inside under the square root must be non-negative. In other words, the domain of f is nothing else than just this interval 0, close, will include 0 and positive infinity. So the restriction will be that x cannot be negative. So that cannot happen under real numbers, right? All right. Now let's see some other examples. So let's say this is okay, a. Let's see some other square roots. B. Let me take the following one. F of x is the square root of 2 times 3x plus 1. So you see you have a little bit more complicated example. Well, I wouldn't say it's that complicated, but it's just a little bit. Well, as we have said earlier, and as you can see here on the screen, that the values inside the square root must be non-negative, right? So in other words, the domain of f is, let's write it in words, is all values of x, all x values, let me put it this way, such that the quantity inside is non-negative, such that 2 times 3x plus 1 is non-negative, right? All right, that's great. And now we can solve this inequation, which we did in the previous lecture. So let's solve it. This implies that this implies that 3x plus 1 is greater or equal than 0, or equivalently, x will be greater or equal to -1/3, right? That's easy to see. So the domain will be the interval -1/3 closed and positive infinity. So that's the domain of the function square root of 2 times 3x plus 1. Okay, now let's see some other examples. Let's see a third one, which will be a different type of example. And the one, what I would like to say now is, I would like to take this function, f of x is natural log of x. Sometimes we denote it by ln of x, but also log is some. If I use this notation, log throughout the semester, sometimes you can just this implies that it's the same as ln, so it's the natural log. But anyway, you can use any notation you want. It doesn't really matter that much. So we're going to take this function, f of x is ln of x, and the domain of this, again, the quantity, the domain will be all positive reals x, or you can say it's open 0 is the interval 0, open, and positive infinity, right? So this is the domain for the natural log. So the quantity inside the natural log, when we're talking about real numbers, has to be a positive, right? We don't want to deal with ln of negative numbers or anything crazy like that. Okay, now let's, this is the first example. Now the second one, let's take f of x is ln of x minus 3. So we have said previously that the domain of ln of x are all positive real numbers. And well, in this case, the domain is nothing else than all the quantity here. If we look at the quantity here inside, right, this quantity has to be positive. So the domain will be all these numbers for which all these values x for which x minus 3 will be positive, which implies that x is greater than 3. So the domain, in fact, is nothing else than just 3 positive infinity, right? Open interval. Well, anything below 3 is not going to work. For example, if you will plug the values x equals 2, it's not going to work. You will get an ln of negative 1. So that's not going to work for real numbers. And now we've talked about the domain. I would like to see something about, let's see, domain, okay? And now I would like to see something about the range. And let me draw a picture here so that things are a little bit clear. So before I even draw the picture, let me say that the set of all images of elements of x of the set x, right? This is what the range is. And now let's draw a picture so that you can see it better. Let's just take here one domain. Let me take here another one. All right, great. This will be x, this will be y, right? And we have a function from x to y. So I'm going to take elements from here, and I'm going to put them somewhere in here. Let me take another element. I'm going to have here, and then I'll put it somewhere here. And here I will create an, okay, maybe I shouldn't. Maybe inside this, I will create this smaller subset. We'll call this, this will be the range, right? Okay, and now let's take more elements. Here, let's say I will take one from here. So all of these are going through the function f. Keep that in mind. So this function f takes elements from the domain from x, and they will be sent in this codomain in y. Some of them will be in the range, some others will not be in the range. And let me take some others, maybe here, maybe here, maybe here. There are some elements here, maybe here. But I'm only going to take elements that will be sent into the range. Again, this is through function f. So basically, this is the domain x, and well, this is going to be the range, right? So this is the codomain y, and now we will have the range. Anyway, we'll see the difference between these two as we see some more examples. In fact, let's see some examples. All right, the first example, examples 1, find the domain and the range of the following function. F of x is x minus 2 over x plus 4, and this x is, let's say, the set x for which this is defined consists of this element, so it's a discrete set, -3, -2, -3, 0, 1, and let's say 1.5. Okay. So know that the domain is already specified in the problem, right? So this is the domain, right? It's already there. And now what we need to find is the range. As you can see, this is a discrete domain. It has assigned those values. There are like 1, 2, 3, 4, 5 values. So we need to evaluate these 5 values through the function f. And once we do this, so to find the range, right, we evaluate f at the values from the domain x, right? And now let's plug in for each one of them. We'll evaluate f of -2. Well, if you plug in f of -2 there, this will be -2. F of -3 will be let's see, -5. F of 0 will be -1/2. F of 1 is -1/5. And f of 1.5, 3/2. This would be 0.5. This would be -1/11. Okay. So the range is, let's call this range, right? Will be these values, -2, okay, -5, sorry, let's take it, -5, -2, -1/2, -1/5, -1/11. So that's the range of f. And now let's draw a picture so that things will become clearer. This is the domain. This will be the, so this is x, the domain. This is y. We'll call this the codomain. And now let's see, let's identify the range here, because this will be just a few elements here. So this guy will be the range. And now let's see here, we have these elements. Let's say we have -2. This guy is -3 somewhere here, 0, 1, and 1.5. So these elements are sent by my function f. Each one of them, they're sent somewhere here, right? Okay, so these are sent here, right? Through the function f. And here we will have the following elements. We'll have again -5, -2, -1/2, -1/5, and we'll have, say here,-1/11, right? So this is what we have. And all of these are obtained through the function f. Okay, so this is the picture. That's why I think it's quite clear. Now let's take another example. A second example. For example, let's take the following function. F of x is x minus 2 over, we're going to take a rational function over x plus 4, right? All right. And I would like to say one thing here. Note that the domain is not specified, so we need to find it. Let's see, what restrictions do we have? So we have that x is different than -4 because, as we said previously, for this function to exist, we need to make sure that the denominator is non-zero. All right, so the domain is nothing else than just the entire real line. So it's -infinity, infinity, and we exclude this value, -4. Or if you want, we can write this as a union of two intervals. So it's -infinity and -4 open interval united with union with -4 and positive infinity. So that's the domain of this function. And now we need to find also the range of this, right? Note that x minus 2 is different than x minus 4 for any possible x, right? So any x you plug in there is not good. That fraction will never be 1. So this means that f of x is cannot be 1. So it's different than 1. So therefore, the range will be nothing else than just the entire real line is -infinity, infinity minus this element 1. If you want, you can write it in this way: -infinity 1 union with 1 positive infinity. So that's the range of this function. Well, let's take another example, a third example. Let me take a little bit more complicated example. F of x is the square root, and I'm going to take a quadratic function here. Let's say x squared minus 5x plus 4. Right? So let's analyze this. And we need to find a domain. And keep in mind, so to find the domain, we need to make sure that the quantity inside, so let me say it again, the quantity inside the square root is non-negative, right? So to find the domain, we need that x squared minus 5x plus 4 is non-negative. Well, let's rewrite this. Let's explore this inequality a little bit more. So this is equivalent with, and now let's factor this. And we can factor this with x minus 4 times x minus 1 greater or equal than 0. Right? So it's equivalent with this. So we have a couple of options here. So we have the product of two numbers being non-negative. So we have a bunch of options. Both of them have to have the same sign. So this means that either both of them are negative or both of them are positive. So there is no other way around. In other words, let me just say it. But so Let me draw a picture first of all. So we have this negative infinity, infinity. And we have these values here, 1 and 4. And guess what? In other words, if I look at this interval, negative infinity 1, then, well, the inequality holds true because, so we divide this in 3 intervals, negative infinity to 1, then what happens between these two numbers, 1 and 4, and then from 4 to infinity. Between negative infinity and 1, you can just plug in 2 values for that. For example, if you put, so you have both of them here. So both of them are negative, right? We have negative times negative, which will be positive. So the inequality holds. Okay, now let's see between these two on this interval, 1 and 4. So you'll have one of them will be negative, the other one will be positive, and when you multiply that, this will be negative. The inequality does not hold. And now, if we look on this interval for positive infinity, we'll have both of them to be positive. Again, the product will be positive, so the inequality holds. So in other words, the only problem where we have is right here. So here it doesn't hold. Let's put an X here. There is no way we can have a value for X between 1 and 4 so that this inequality here to be true. So there is no way such a thing can happen. All right. Well, this implies the domain, that the domain is nothing else than just this union of 2 intervals, negative 1, 1, and close at 1, union with this interval 4 and infinity. So that's the domain. Well, the range is quite easy to see. Again, this function gives all positive square roots, right, for these values. So the range, let's write it like this, the range is nothing else than just 0, closed, and infinity, right? So this is one of the problems, right? How we, and now let's talk a bit about functions, and we'll see more examples. We want to see which ones are functions, which are not functions, and let's point out some remarks. Okay, first of all, not all mathematical expressions are functions. So let's keep that in mind. Also, a second remark is that it is possible for 2 different elements in the domain, for 2 different elements in the domain X to be mapped into the same element in the range. Right? For example, let me draw a picture so that everything is clear here. So I have two elements here in X, so this is X, and I want this. Let's say this is Y, this is, and here we have the range, let's say smaller, right? And let's just say that well, I have a bunch of elements here in the domain. Let's say some of them, this is mapped here, so it's this guy will be mapped here. Everything is mapped through the function f. This guy is mapped somewhere here, but also this guy is also mapped in this here. As you can see, there are two elements which are mapped in one element in the range. So this can happen. We'll see that. We'll see functions which have this property. Okay, the third one is that it is possible for Y, the codomain Y, to include elements which are elements which are not in the range of f. Right? We can have some elements here. Okay. The fourth remark is that the range of f does consist of all elements well, the range of f does consist of all the elements, okay, all the elements of Y. Then f is said to map, and we're gonna X onto Y. Right? And we'll see that this these kind of functions, they have a property. So this, we call this functions onto. Anyway, the fifth one, if each element in the range if each element in the range is the image of one and only one element this is very important, of one and only one element in the domain, then f is said to be a, we'll call this one-to-one function. One-to-one function. Anyway, we will see also the formal definition as we proceed. Let me draw a picture here so that things will be clearer. Okay, so we have this here. This will go to an element here. Also here. So this is what we call one-to-one correspondence. And I think it's obvious why we call it like this. It's just one-to-one. As you can see, it's one from here maps into one here. And so there's one-to-one correspondence. There is no way you can map the two elements into one. So that's why we say one-to-one correspondence, right? All right. And now the sixth one is that it is not possible to have two elements in the range for one element in X. So that cannot happen. So you cannot map one element from the domain to two elements in the range. Anyway, let's see some exercise because I want you to see which ones to identify some functions. So the question is the following: which of the following are functions? Well, if affirmative, identify the domain and the range. All right, let's look. I will draw the following chart. So here I'll have expression. Here I have, okay. Does this represent a function? So it's okay. Well, if affirmative, we said we want to see what is the domain. And of course, we want to see also what is the range. Okay, so this is these are the questions we want to answer. All right, let's start with the first example. Now let's take this function f of x is 2x squared. Right? Well, is this a function? Absolutely yes. Well, what is the domain? Well, clearly you can plug in any value for x. It's negative infinity, infinity. It's the entire real line. And the range, well, guess what? Since x squared is positive, is non-negative for all values, all real values of x, this will be nothing else than just 0, infinity. All right, okay. Now let's take another function. Let's take one that it's a little bit more complicated. 3x cubed this time minus 5x minus 2x, sorry, plus 5. Well, is this a function? Well, yes. It's quite clear that this is a function. Well, the domain again, well, we can plug in any value for x, any value you want for x, so you won't have any problems. So the domain will be negative infinity, infinity. And then, well, the range clearly is the same thing, negative infinity, infinity. since you plug in, you don't have any restriction for this function. As you can see, it's a polynomial function of degree 3, so you wouldn't have any problem with it, right? Okay, now let me take another one. F of x is plus minus square root of x. Well, is this a function? Well, not quite. Because we have to define it in a certain way, not it's negative x, it's positive x. So here we don't need to, okay, right? So these are the examples. Well, I would like to say, maybe I should say a bit more with this no here, because, well, there are two values in the range. For example, if you plug in x equals 4, right? So you have plus minus square root of 4 will be plus minus 2, right? So basically, so let me just explain it a bit more here. No, because, for example, if we take x equals 4, you will have that f of 4, which is plus minus square root of 4, will give you plus minus 2. In other words, you'll have here the domain, you take this value 4, and guess what? When you send it, you'll send it to two values in the range, which will be 2 and negative 2. That cannot happen. This contradicts clearly remark number 6, where we said that it is not possible to have two elements in the range for one element in the domain. So keep that in mind. This is important. Okay. And now let's take another function. This time I'm going to take the following. F of x is square root of x. Well, is this a function? Absolutely yes, we said that. And the domain will be, well, clearly 0 closed positive infinity, and the range will be the same thing, right? Because this is just a non-negative square root. Okay, I think this clears up a bit the picture of which one is a function, which one is not a function. Right, and now we would like to see something a little bit more. We would like to evaluate some functions at some particular values, right? So let's talk about evaluating functions. Right? Okay, now let me take some examples. So evaluating a function, what does this mean actually? It means, so evaluating a function is nothing else than just finding the value of f for some particular value in the domain. So that's what we mean by that, by evaluating a function. Okay, let's see examples. And now I will have some quick examples for this. Let me just take the function f of x to be 2x squared minus x. Now let's evaluate let's say f of 0, which is clear what we plug in x equals 0, so it will give you 2 times 0 squared minus 0, which is 0 minus 0, which will give you 0. Let's say we want to evaluate f of 2, which will give us 2 times 2 squared minus 2, and this will be nothing else than this is 4 times 2, which is 8 minus 2, which will give us 6. Let's suppose now we want to evaluate, well, instead of plugging some numbers, we want to evaluate f of x plus 3, right? We know what is the expression for f of x. Now we're going to shift it to the right by 3, which will give us x plus 3, and this will be 2 times, instead of x, we'll replace by x plus 3, so it will be x plus 3, everything squared minus x plus 3. And now we should be a little bit, we should pay attention with the computations at this point. And this will give us, well, you can expand this. This 2 times, using the expansion, the square expansion, we'll have x squared plus 6x plus 9 minus x plus 3. And this will give us nothing else than just 2x squared plus 12x plus 18 minus x minus 3. And this is 2x squared minus plus 11x plus 15, right? So that's the expression. Anyway, and you can evaluate anything you want though, so I believe there is no problem. You can take any function you want. It doesn't have to be a square function. You can take a polynomial, whatever. Now, I would like to talk to you about a different type of evaluation. And this evaluation will be very important when we will talk about derivatives later on. And what I mean by that is the following. Let me talk about the difference quotient. I think I mimicked in the first lecture when we took that. You remember when I gave you the example with Aaron and Alex, they just want to jump off the building, and they're wondering what happens at that moment, t, but t equals 1. So anyway, and we basically mimic the difference quotient, which nothing else is. Let's call it, I'm going to denote it by this, d from difference quotient, dh of f, which will be defined in the following way, is f of x plus h minus f of x over x plus h minus x. Right, in the first lecture when we talked about that example, h was delta t, in fact. And if we look a bit, sorry about that, and if we look a bit closely at this expression, and if we do the algebra, this is nothing else than just f of x plus h minus f of x, everything over h, right? So this is what we call, this guy right here, is what we call the difference quotient. Okay. And this, like I said, will be very important when we'll talk about derivatives later on. I think that would be chapter number 3. Now let's take a function. In fact, let me take the function, the previous example. Let me take this one here. F of x is, for example, compute the difference quotient for the function f of x equals 2x squared minus x, right? That's what we want to do. Okay, let's do it. This is pretty straightforward. I want you to look at this formula here above for the difference quotient, and that's what we're going to do. So the difference quotient, like we denoted as dh of f, is nothing else f of x plus h minus f of x, everything over h. Okay, let's plug in the values. Let's compute this. So this is remember that we're going to replace x by x plus h. So we will have 2 times x squared will be replaced by x plus h squared minus x plus h, right? Let's put it like this. Right, so this guy here is f of x plus h, right? As we can see, we don't have x plus h instead of x, and now, so this is over h, and now minus f of x, which will be 2x squared minus x. And this guy here is nothing else than f of x. Okay, so this will be equal to, and now, we have to do the computations. That's not a pleasant thing to do, but anyway, we'll have to do it. Okay. Well, we can do, we have plenty of options here, but I'm just going to do it in the safe way, where I'm just going to expand everything. So it will be a little bit of work, but we can do this. This will be, let's work on the first parentheses. So this would be 2 times x squared plus 2xh plus h squared minus x minus h minus, and now let's change the sign, negative 2x squared plus x. All right, beautiful. And now this will be equal to, let's write it here. So this would be 2x squared plus 4xh plus 2h squared minus x minus h. Okay, minus x minus h minus 2x squared plus x, which will give us over h. And this is, so these guys will just go away. These guys again will go away. And we're left with the following: 4xh plus 2h squared minus h. Everything over h. Well, guess what? As you can, if you look at the on the top of the numerator, we can factor an h there. So this would be nothing else than just h times 4x plus 2h minus 1 over h. Now we can cancel these two, and this would be nothing else than just 4x plus 2h minus 1. Of course, when h is different than 0, let's keep that in mind. Right, when we cancel this, we have to make sure that we are not canceling with 0. But anyway, that's the thing that we will learn in the next chapter, is that we will take the limit as h approaches 0, and then we'll find the derivative of this. So guess what? This will give us that when h is 0, this expression, when h approaches 0, this expression, this difference quotient, will give us 4x minus 1, which is nothing else than just the derivative. But anyway, let's not rush through things. We will see what the derivative is all about in chapter number 3. But I wanted to show you how to compute the difference quotient of a function. Well, this is a quadratic function. All right. Now let's talk about some other types of functions. And let me talk about piecewise functions. Right? So certain functions are defined differently, right, on different parts of their domain. And well, it's natural for us to express in terms of more than just one formula. For example, that I have in mind is the following: f of x is, now let me take this x times sine of x if x is less than 2. And so this is one branch of the function. This is what we're going to say. And the second one is 3x squared plus 1 if x is greater than 2. So this is what we call a piecewise function. Just like we said, it's expressed in differently on different parts of their domain, right? As you can see on this part of this domain, for example, on this part, when x is less than 2, it's expressed in this way. It's x sine of x. And on this other part of the domain, well, specifically for all values x greater or equal than 2, it's expressed in this way. Okay, and now let me a quick question. Evaluate, let's say f of 4, f of pi over 2, and let's say f of 1. No, f of 3, let's say. So we want to evaluate these values through our function f. And well, you have to look how the function is defined. Like I said, it's a piecewise function. So you need to look at it very carefully. Okay. All right, let's see. The first one, f of 4. Let's look at the first one, f of 4. Let's see where 4 is. Well, 4 is somewhere here in this domain. So here where 4 is. So it includes the value 4, right? So f of 4 will be 3 times 4 squared plus 1, which will be 49. All right, let's look at the another one, f of pi over 2. Well, pi over 2 is 3.14, well, approximately, divided by 2, that will be 1.50 something, right? So in other words, this is where we look for pi over 2, because it's pi over 2 will be here, and in the first branch, so it will be on the interval negative infinity 2. So we will plug in for this function. So it will be pi over 2 times sine of pi over 2, and which will give us pi over 2, right? Keep in mind that sine of pi over 2, as we have seen in the previous lecture, is 1. And now f of 3, if you want to look for f of 3, this is nothing else. Well, let's see where 3 is at. Well, it's the second one. We have 3 here. We'll have 3 and 4. Okay, let me put it this way. 3 and 4. So we have them here. So f of 3 is nothing else than just 3 times 3 squared plus 1, right? Which will give us 28. Okay, beautiful. This is how we operate with piecewise functions. And like I said, these functions will be very important when we'll study their continuity. We will see that we want to study the limits of these two branches. They have to match up at a certain point. Anyway, we'll get there when we'll talk about, probably in the next chapter, when we'll talk about limits and continuity of functions. We will see how important these piecewise functions are. Now, let me talk about something else. Let me talk about the composition of functions, because this will be important. All right. Well, the composition of functions is defined in the following way. So we will define it in this way. F circ G, right, of X. We'll write it in this way, which by the definition, so right here, definition, def, is nothing else than f evaluated at the function g of x. It won't be evaluated just x, it will be evaluated at g of x. Wow, that's quite something. right? And let me give you an example real quick so that you can see how we operate with this composition. So we will read this f composed by g, right? Okay, let me give you the example. Let's say f of x is 3x plus 5, and g of x is square root of x, let's say. And I'm interested to find f composed with g, right, of x, let's say, and g composed with f of x, right? So let's see. Well, by the definition, if you look at it, we said that f composed with g of x is nothing else than just f of g of x. And now I'm gonna look. I'll be looking at 3x plus 5. So, and I'm gonna instead of x, the argument x, I'll have g of x. So this would be 3 times g of x. Let me write it in this way. 3 times g of x plus 5. So as you can see here, I'm just replacing x by g of x, right? All right. Now let's look who g of x is. So this will be 3 times square root of x plus 5. Okay, which is 3 square root of x plus 5. That's it. That's the function. Now let's look the other way around. G composed with f of x. This is nothing else than g of f of x, which is nothing else than just, now I'm going to write, this will be the square root of x. But instead of square root of x, I'll put f of x. So this will be the square root of f of x this time, as you can see here, right? So the argument instead of x will be f of x. And now this guy will give us the square root of, well, f of x is 3x plus 5. So that's the square root. You see, as you can see, f composed with g is not the same as g composed with f. There are two different things here. I want you to look very closely at them. This is not the same thing, right? Okay, so this is how the composition of functions will operate. And now let me talk about let me draw some graphs, how the graphs of a function. Let me talk a bit about this. So, graphs of functions. Okay. Well, what is the graph of a function? Well, we have, let me draw a picture. We have seen this plenty of times. Let me say I have a function that goes like this. So the graph of a function of f will consist of points whose coordinates, let's say, so this is the x and the y coordinate here, right? So this is a point, let's say m on the graph of the function of coordinates x, y. So the graph of a function of a function f consists of points whose coordinates, let's say x and y, satisfy, so the coordinates x, y, let's say, of that point m, will satisfy this y equals f of x, right? So this is the graph of a function. This is, well, okay, this is y equals f of x. And we have this point m on the graph of that, right? So that satisfies y equals f of x for all x, all values x in the domain of x, in the domain where f is defined, let's say. The domain of definition of f. Okay. Now let me draw some pictures. For example, some examples of graphs of functions. Okay. Let's see. For example, the first one, let's draw a line. We have seen this already. I'll draw a line. Oh, it didn't go through the origin. Anyway, so this is a line, right? Well, let's take it through the origin. Let's say this is, okay, let me draw it again. So it will go like this. This is y equals x. So this is the line, right? Okay. Now let me draw something else. For example, let me draw a parabola this time. So this will go like this. It will go, oh my. It will go like this. Okay, this is not quite a parabola, but anyway, this is y equals x squared. So this is a line. This is a parabola. Now let's see if we want to graph a cubic function, the simplest cubic function, y equals x squared. It will be something like this. Right, so this is y equals x cubed. So this is the cubic. Anyway, and so on. We can draw the absolute value if you want. Okay, let's draw that as well. So this is y equals absolute value of x. And so on. Anyway, we can draw different type of functions. We can draw the square root. We can draw the inverse of the square root, the inverse of the linear function, and so on. Anyway, I think I have an example in my notes. If you look at in the notes, there is an example of functions and graphs, and there is a table with many functions and many graphs. And you'll find it in my notes. I don't want to lose too much time with this, so I want to cover more material. Anyway, I think, whoa, we've been over time. Anyway, and now I would like to say a few words about other properties of functions. For example, how do we identify a function graphically? And can we interpret some of the properties of a function by just looking at it? Well, there's one thing that one way to identify a function. Well, there are many ways, but for example, we can do, so the question is, how do we identify a function graphically? That is a question we want to answer. Well, the first thing is that we'll want to, it's the vertical line test. And what is this about? Well, a curve in the plane is a graph of a function if and only if, so I'll write like this. This guy is if and only if from now on. Well, I'll put two f's. So from now on in lectures, this will be if and only if. It intersects no vertical line more than once. Right? So let's draw a picture so that you can see it. For example, so let's say we have a function like this, and let's just draw some vertical lines here. It will intersect the graph in only one point. Right? You can see here, right? So it doesn't, so any vertical line that you see intersects the graph only just once. For each value x, there is a unique value y, right? So this graph indeed represents a function. This graph is a function. So it does indeed represent a function. All right, now let's see another picture. All right, let's draw the same picture. Well, not quite the same, you will see. All right, now let's just say I have a curve that goes like this, right? As you can see here, if I take a vertical line, all right, and this vertical line here intersects the graph of this in 2 points. Well, at two points, right? Just look here. In these 2 points, and let's just say this is the line C. So for x equals C, there are two y values. So this means that no unique y value, that we don't have any unique y value for x equals C. So this does not represent a function. Okay, so this is not a function. All right, so this is a vertical line test. Now we also have, as you can imagine, the horizontal line test. Anyway, you will see throughout the semester plenty of other ways of finding properties and to test a function so that you can, in such way that you can actually draw the graph, but then we have to know something about derivatives, something about the asymptotes, and so on. So I'm not going to go into details at this point, since you will see them as we go, as we dive in and we see more material. All right. Well, the horizontal line test is very good to identify one-to-one functions. Well, we say that a curve in the plane is a graph of a one-to-one function, and this is very important, if it passes with, okay, the vertical line test and if no horizontal line intersects the graph at more than 1 point. And this is important, more than 1 point. So there is no way something like this can happen, right? So look again, the horizontal line test. And now let me draw a picture again. Right, these are the axes. All right, let me draw the following picture. Right, this is the graph of a function. And let's just say I'm going to take some vertical lines here. Now some horizontal. Okay, let me draw it again. Okay, here I'm going to take a horizontal line, right? As you can see, if we, this graph passes the vertical line test, right? So the graph indeed represents a function. But however, if you look closely, the horizontal line intersects the graph at 2 points. You see this point here and this point here, right? If we look at it. Well, what does this mean? We've said earlier, this means that the function is not one-to-one. So this function, this is the graph, this is a graph, right? The graph of a function which is not, and I repeat, not one-to-one. Right? Just like we said, if you look at the horizontal test, right? We said this clearly. So look at it. You can see the graph of this intersects the horizontal line in 2 points. So there is no way we can have this function to be one-to-one. All right. Now let me draw another picture so that you can see it better. And this time I want to take a one-to-one function. Let me draw it like this. So this is a function, goes all the way down, all the way up. Well, if you look at it, is this a function one-to-one? Well, if you look at it, this graph passes both vertical and horizontal line tests, right? So this is indeed this is the graph of a function which is indeed one-to-one. Keep in mind that. So I want you to look again at this horizontal line test. So again, a curve in the plane is a graph of a one-to-one function. If it passes the vertical line test, well, of course, it has to pass so that we can look at this as a function. And if no horizontal line intersects the graph at more than 1 point, so it has to be just 1 point, no more than that. And we have seen examples. Now, another thing, well, we've talked about the vertical line test, horizontal line test, but also I'd like to talk about something else which is very, very important. And that thing that I want to talk about is how do we find the intercepts? So finding intercepts. Okay, the y-intercept, right? And the x-intercept, right? So what is the y-intercept? So these are the points on the graph that intersect the y-axis. Pay attention. And the x-coordinate of the y-intercept is always 0. So keep in mind this. The x-coordinate of this y-intercept is always 0. Okay, and now we would like to see what happens. So as you can imagine, a similar thing will happen to the x-intercept. Well, these are points where the graph intersects the x-axis, and the y-coordinate of the x-intercept is always 0. So it's the same thing. We just replace the x with the y. So the y-coordinate of the x-intercept is always 0. Okay. Now let me draw a graph. We have, and I'm going to draw it in the following way. So I'm going to go like this. Okay. This is my function. As you can see, it will intercept here. This is the y-intercept. Coordinates 0, a, let's say. So this guy is y-intercept. Again, it will intercept at these 2 points, and this will be the x-intercept. Let's say this will be of coordinates b0, and this will be of coordinates c0. So these 2 guys, this is the x-intercept, right? So, okay. So this is how we, well, there are examples. We can look for them in my notes. So now let's talk about something else, about symmetry. Okay. Symmetry. Well, let's see what it means to be symmetric with respect to y. Respect to y, right? We want to see what that means. Well, we will look at this graph. We say that the graph y equals f of x, right, is symmetric with respect to y-axis if whenever, let's say this point P of coordinates xy is a point on a graph. Right. Well, when this is whenever this is a point on a graph, so is the point. Let's say Q of coordinates negative xy. Right. So we will call this the mirror image. This point Q will be the mirror image of the point P, right? And we will say that y-axis symmetry occurs if and only if f of x, and this will be very important, f of x is the same as f of negative x, right? Well, such a function is called an even function. This is what we call even function. If a function is even, then if a function satisfies this property here, then we say that this is an even function, right? So this is the symmetry with respect to y, and now let's see what it means. Well, symmetric. What it means to be symmetric with respect to the origin. To the origin. All right, the same thing, the graph y equals f of x is symmetric with respect to the origin. If whenever the point p of x of coordinates p of x, y is on the graph, so is the point, let's call this R, of coordinates negative x, negative y, right? So this, which is this guy is the mirror image, let's write it, the mirror image of P with respect to the origin. Right? Well, we will call such a function, so symmetry, let's just say this. So symmetry with respect to the origin occurs when we have this, when f of negative x is the same as negative f of x. And such a function we'll call this an odd function. So we have even and odd functions. And let me draw a graph of these two. So for example, in fact, let me draw two separate graphs. Okay. Okay, hope it makes sense. Anyway, this is a function. No, maybe that's not what I intended. It goes like this, right? So we have this point here of coordinates x, y, and we reflect this. So this will be the mirror, will be negative, or this point will be negative of coordinates negative x and y. So this is what we call an even function. And now let's see an odd function. Well, let's look for something like this. Let's go in this way, right? And here I have a point, here I have a point. Let's just say here I have x, y. And here I have negative x, negative y. So that's the mirror image, right? This is what we call an odd function. Okay, so this is, and now let me just give you a quick example. And I think I'm going to stop here. Maybe I'll do another video with the classification of functions where we will talk about also, because this is getting a bit too long, when I will also talk about trigonometric functions as well. And that the other video will be a little bit shorter than this one. So let me give you quick examples. Okay, the first one, f of x equals x squared. What do you think of this function? Is it odd? Is it even? Well, it's quite clear what happens. If we evaluate f of negative x, this will be negative x squared, which is nothing else than x squared, which is f of x. So this implies that f is even. Let's see another example. G of x equals x cubed. Well, if we look at this, if we evaluate g of negative x, this will be nothing else than just negative x cubed, which will be negative x everything cubed, which will be negative x cubed. So this is nothing else than negative g of x. So this means that f is, g is odd. Right? So these are, and there are some other functions. The third one, let me take this one, h of x, which is 5x squared, x squared plus 5x. And something funny happens here. And if we evaluate h of negative x, this will be negative x squared plus 5 times negative x, which is x squared minus 5x. Well, if we look at negative h of x, this will be nothing else than negative x squared minus 5x. So, whoa, doesn't fit into the picture. So we don't have, h is neither odd or even. And that's it. So not all functions, if a function is even, and it's not odd, or the other is not, doesn't imply that all functions can be even or odd. There are functions, as you can see here, that are neither of these two. Okay, guys, I think I'm going to stop here. Next time, I will talk about more about the classification of functions. Just like I said, I would like you to see what is a linear function, what is a quadratic function, what is a cubic function, and so on, a polynomial function. Also, I like to talk veer towards trigonometric functions. For example, I would like to see, or like to talk about inverse trigonometric functions, and I would like to insist on those a bit. Probably the third lecture would be very, very short. I could have continued now, but I prefer not to because I don't want to go over it too much. Okay, thank you very much. I'll see you you will have another video, so, and I guess I'll see you next week on Tuesday. Bye-bye.